Hello everyone, welcome to our talk. So today Jonathan and I are going to talk about a little bit about fundamental physics project we are starting, and mostly we're going to talk about infrastructure behind it, specifically the SetReplace package and other code we're building. So the basic idea of the fundamental physics project is we are going to try to find fundamental theory of physics using approach of a new kind of science, which means we assume that the universe is produced as an evolution of a simple system, and specifically we want to pick a system that has the least structure, as little structure as possible. So specifically the system we are going to study, at least at first, is what we call the set substitution system. So this is kind of similar to graph rewrite systems or network substitution systems, but it's simpler in a way because all it is that we have a set, an ordered set, as a state of the system, and then at each iteration we take a subset of the set which matches a particular pattern, and we replace it with something else. So we have this function called SetReplace, and for example, if we take set which is 1, 2, 3, 4, we can replace 3, 1 with AB, and we get 2, 4, AB. Of course, we can use patterns in the rule inputs as well. So in this case, for example, we take 2 odd numbers and replace them with a sum. And the interesting things start happening when the elements of the set have some relationship between them. So in particular, a simple case would be, suppose each element of the set is a pair of numbers, which makes it a graph, well, directed graph in particular. And we can take a path graph, for example, and then we can specify rules that will take 2 adjacent edges and replace them with a single edge. And after 2 steps, we just get 1, 4 here from this path graph. And we can do the opposite thing as well. We can introduce new vertices on the right-hand side of the rule by putting a module in it. So in this case, we are creating a new vertex on the right-hand side of the rule, and we replace 1 edge with 2 edges, inserting this vertex in the middle. And we get this structure, we get this path graph where the new variables were created by the module. Now, because it's kind of complicated to write these modules every time, we also have a short notation for these rules, in which case we just use numbers, and all the numbers on the left-hand side of the rule are replaced with patterns, and if the new numbers appear on the right-hand side of the rule, the module is inserted automatically. So in this case, we get the same rule here. Okay, so for running the system for a large number of steps, it's actually more convenient to use another function, which is called Wolfram model. So this is the one we mostly use to analyze the systems for physics purposes. So if you take a rule, we can take a particular rule. Let's see. Let me show you how it looks like. Yeah, which takes 3 edges coming from the same vertex and replaces them with this kind of structure. We can evolve it for 6 steps where, so for Wolfram model, you just specify the rule in terms of numbers straight away. You don't need to use 2 pattern rules. And then each step here means we replace all non-overlapping subsets at once. And then we get this evolution object out of it. And we can ask various things of this evolution object, such as, for example, we can ask it to give us the state of the system after each step. And we get this evolution, which produces things like this at the end. Okay, so there are a number of properties one can ask this evolution object. So one of the interesting ones is causal graph, which shows a network in which each vertex is an event, and we have an edge between the vertices if the output of one of the events overlap with an input for another. In other words, if there's a causal relationship between two events, then we put an edge in between them. Okay, and finally, I want to talk about some visualization functions we have. So we are currently developing. Okay, so first I need to say that we can consider hypergraphs as well in the systems, because the set can contain elements which are not two vertices, but more than two vertices. So for example, in this case, we have ordered hypergraph consisting of 3 edges instead of 2 edges. And the way so we can plot it. And here, okay, so this is what we call brain electrical embedding. So the way it works is that it's similar to spring electrical embedding, except we also simulate these hyperedges together with vertices. And so in this case, we have essentially a path graph consisting of 3 hyperedges. So it looks like that. And if we have, so in this case, we have 2 double self loops, so which is 1, 1, 1, and then 1, 1, 1 on the other side. And then we can have things like that, where it's 1, 3, 3, 3, 5, 5, and 5, 1, 1, and so on. Yeah, so this visualization is not completely implemented yet, so it's not yet in the package, but it's going to be soon. And this is an example of a large graph. As soon as we get it. Okay. So all of this code I just showed you, except for as a hypergraph visualization, is available on GitHub in the SetReplace package, which you can find from this link. So you're welcome to look at it and ask me any questions later. And with this, I give you to Jonathan.
I've got one.
Okay.
Okay, thanks. I'm now going to talk very, very briefly about how we can take one of these sort of set substitution, hypergraph substitution systems and go about deducing whether or not it satisfies kind of reasonable discretizations of known laws of physics. So one thing we have to be able to do if we want to be able to do this efficiently is evolve what are called multi-way systems. So multi-way systems are sort of combinatorial structures that occur when there is no kind of canonical order in which to apply the replacement operation. So effectively, one applies all possible replacement orders, and one gets this sort of tree structure, or hopefully actually not a tree structure, but something a little bit more interesting than that, which represents all possible updating orders. But one thing you have to do if you want to do that efficiently is determine when to set substitution when to sort of hypergraph spatial slices are equivalent, which is essentially a question of whether two hypergraphs are isomorphic. And so fortunately, I worked on this problem actually a few years ago, and so we have now reasonably fast implementations of this so-called uniqueness tree algorithm generalized for the hypergraph case. So here's an example of two hypergraphs that are sort of trivially isomorphic. Here are two hypergraphs that are trivially non-isomorphic. We have isomorphisms can be detected between both ordered and unordered hypergraphs, which are sort of the natural generalization of directed and undirected graphs. So here's an example of two hypergraphs that are isomorphic as unordered hypergraphs, but non-isomorphic as ordered ones. And as well as just detecting the presence of an isomorphism where one exists, we can also return associations that sort of that indicate the presence of those isomorphisms and indicate kind of which vertices can reasonably be mapped onto which other vertices, given the particular hyperedge configuration that you specified. So given that, we now have a way of evolving these multi-way systems. So let me actually do that. So let me do this for 4 steps. So here's a multi-way system for this particular set substitution rule. And this is what we get. It bifurcates after a few steps. So let's do this for a little bit longer. and hopefully we'll get something interesting. So we start to get something a little bit non-trivial here. So you see that there are a bunch of these bifurcations where there's kind of ambiguity in the updating order, and then there are places where these points reconverge, that effectively different updating orders lead to sort of spatial hypergraphs that end up being isomorphic. In this particular case, they're being treated as ordered hypergraphs because that's sort of the main system that we've been investigating so far. And so Max already mentioned this notion of a causal network, which is kind of the discrete analog of a space-time for one of these things. If each hypergraph is essentially a space-like hypersurface, then the causal network is the sort of gives you the conformal structure of the entire space-time. So one question you can ask is, if you have a multi-way system, does every branch of the multi-way system yield a causal network or do all branches of the multi-way system yield causal networks that are all isomorphic as undirected graphs? This is a property that Stephen first referred to in NKS as causal invariance, and it's related to the so-called confluence or Church-Rosser properties of abstract rewrite systems. And it's interesting because at least in Stephen's conception of fundamental physics, this property of causal invariance turns out to be equivalent to Lorentz invariance, because effectively different possible updating orders correspond to different possible foliations of the causal network into space-like hypersurfaces, and the constraint of causal invariance is precisely the constraint that the ordering of time-like separated events is invariant under the choice of hypersurface, even if the ordering of space-like separated events is not. So thanks to our efficient multi-way system evolution code, we actually have also a very efficient way of determining whether a given candidate universe is causally invariant. It essentially has to do with computing what are called computing all critical pairs, effectively all bifurcations of the causal network, and then determining whether those critical pairs will resolve after a finite number of steps. And there are a bunch of properties of sort of abstract rewrite systems that we kind of exploit in order to do that. So here, this is an example of a multi-way evolution system that ends up being causally invariant and hence consistent with special relativity, even though it's kind of doing all of this complicated bifurcation stuff. And the reason for that is that although it has a lot of these critical pairs, a lot of bifurcations, it turns out that if we just run this computation, we determine that all of them eventually resolve. Okay, here's a trivial example of a multi-way system. I don't know why that vertex ended up being so big. That is actually non-confluent and hence non-causally invariant because it has a bifurcation that ends up not fully resolving. Hang on, I'm not sure what happened here. Something's gone wrong with the visualization, but okay, let me try this. This one will work. Yes, okay. Forget that example. We prepared it about 5 minutes before the lecture. So here's actually an instance of a set substitution system that Stephen discovered in one of his various enumerations. It seems to do extremely bizarre things, and it produces a causal network that has a very rich structure with, say, lots of bifurcations, lots of sort of reconvergences, but it's not entirely clear what's happening or if what's going on is actually relativistically invariant. But it turns out that, it's a reasonably crunchy computation to figure this out. It turns out to be non-causally invariant in this particular case because there are certain critical pairs of this rewrite system that end up not fully reconverging. Okay, so is there a generalization of this approach? Well, there sort of is. One thing is that if we want to do this search systematically, we want to use something that's kind of better for better than heuristics for determining whether a candidate universe is kind of hopeful or not. Because if you have a heuristic, it's going to miss things, and it would be really, really embarrassing if we actually missed kind of finding our universe because of a faulty heuristic in one of these enumerations. And so instead what we want to be able to do is have kind of provably hopeless cases. So there are a bunch of cases where just on the basis of the combinatorial structure of the rule, we can determine things about whether it even has a hope of being consistent with certain laws of physics. So one of these is causal invariance, as I already mentioned. One of these is whether the network limits to a kind of fixed dimensional manifold. So okay, this gets a little bit complicated in that there are sort of discrete Riemannian geometry kind of ideas that I'd have to explain in order to detail this fully. But essentially the idea is, thank you, if you're given a network and you want to determine kind of what's the dimensionality of the space that it might represent, one way you can do that is you just pick a point and then you go out, you assign every edge a sort of unit distance, and you figure out what's the total number of vertices that you can reach from a distance r of a given vertex. And then, for a network that corresponds to two-dimensional space, you expect it to grow like r squared. For three-dimensional, you expect it to grow like r cubed. And generally, in d-dimensional space, you expect it to grow like r to the d, which is true if it's a kind of flat space. In the two-dimensional case, that would be a network that's just a kind of just a trivalent network of hexagons. But if you add in pentagons or heptagons that correspond to the discrete notion of positive and negative curvature, then there's a correction factor. And the correction factor turns out to be proportional to a discretization of the Ricci scalar curvature called the Olivier-Ricci curvature. And then then you can go a little bit further and you can look at kind of growth rates of volumes of space-time cones in causal networks that turn out to be proportional to projections of the discrete Ricci tensor, and you can derive a whole bunch of constraints on this, and they turn out to be equivalent to the Einstein equations. So because of that, we have ways of determining, given a set substitution system, it doesn't have a hope of satisfying the Einstein equations. And one of the key postulates that you need in order for that whole derivation to work is that the causal network has to limit to a finite dimensional manifold. And so we need to have efficient ways of determining whether that's true without having to evolve this rule for potentially millions of steps before we discard it. So one approach we have to doing that is using automated theorem proving algorithms. So basically taking some of the automated theorem proving infrastructure we already have in the Wolfram language and generalizing it to the case of hypergraph substitution systems, which are just like any other kind of substitution system. And hence, by having a kind of specialized network logic with the axioms that correspond to these set substitution systems, we can actually prove theorems about them without having to evolve the whole system. So at least in certain cases, or in a large class of cases, we can prove very quickly that, okay, the causal network that's going to be generated by this particular set substitution system is not going to be compatible with causal invariance. Or we can say that the manifold that limits out of this is not going to have a fixed number of dimensions. Or, so some cases that might be easier to sort of understand would be if we can prove that the causal network for a given set substitution system is always going to be a tree, that's another way of saying that there can be no non-trivial interactions between distinct points in space. And so we can kind of discard that without too much hassle. Or another instance of a situation where we know that there can be no interesting sort of interactions would be one where we can prove that the set substitution system produces a spatial hypergraph which could also have been produced by a neighborhood-independent substitution system, because effectively that's saying that there are no local interactions that occur in that universe. So that's another case where we know it's hopeless. So to do that, we've introduced this, we're starting to introduce a whole bunch of these automated theorem proving algorithms. So here's an example of a set substitution rule that in this case corresponds to a simple undirected network substitution rule. And here's a particular pattern that we want to be able to show always occurs, independent of how the rules overlap and independent of how the pattern is embedded into the rest of the network. That's something that if you were just told this fact and asked to determine whether or not it was true, it would take you quite a long time, even if you had a computer to kind of evolve this thing to determine whether that was actually valid, because there are a lot of different ways that the rules can overlap with each other. There are lots of different ways that this pattern can be embedded. But fortunately, we have these algorithms now, which, with a reasonably short amount of time, can synthesize these formal proofs. This particular one happened to have 41 steps in it. We get back the symbolic proof graph that shows the chain of deduction there. And so now, in this particular case, that means we can discard this universe kind of with impunity, right? Because if we want to, we could have some kind of universe landfill where we just say, this is universe number 231, provably not our universe, and we can actually specify the proof graph as a kind of seal to say, you can go verify this if you want, and you could run the proof function and confirm all of this stuff. Okay, so I think that's everything we want to say, at least for the moment. So, we ought to say perhaps Stephen is planning to make an announcement about this project at some point, I think in the next couple of months. And once we do that, a lot more of the information about the actual physics of these models will become available. Right now, we've tried to keep this talk reasonably focused on the actual kind of underlying software infrastructure and the tools that we're using for searching and filtering these universes. But hopefully, there'll be more information about the actual kind of underlying network science of these things available in the near future. And Max, is there anything else you wanted to say? Or? Okay, well, thank you very much.